Okay, Assalamualaikum and good day everyone. So let's continue with our lesson in instrumentation or biopotential amplifier. Let's focus on the instrumentation amplifier. We can say that the instrumentation amplifier basically it's just like a premium version of amplifier. So it is can do the job such as the current sensing and sensor signal conditionings, and it is a better job at doing a specific signal conditioning, right? So the main task of this instrumentation amplifier, we have 3 points here. So the first one is to sense the voltage between two measuring electrodes. The second one is to reject the common mode signals. And the third one is minimizing the effects of electrodes polarization over potentials. So I have mentioned in the previous lecture. So we have the instrumentation amplifier is basically a combination of a buffer stage and differential stage. So it can sense the voltage between two measuring electrodes. So one of the electrodes is connected to a non-inverting terminal, and the other one electrode connect to the inverting terminal. So this voltage difference will be measured by this instrumentation amplifier, and it also has a very good CMRR. So it must one of the features of the instrumentation amplifier is that it must have a good CMRR, common mode rejection ratio. So it must reject the common mode signals, because these common mode signals usually have higher amplitude as compared to the biosignals that we want to measure. And the third one is to minimizing the effects of electrode polarization over potentials. So when we use the electrodes, somehow there will be effects of electrodes polarization that will affect the signal's resolution. So we want to minimize all these things. So that's why we use the instrumentation amplifier, because it has a very good features at all these 3 points. It is a solution to both high gain and high input impedance problem. It uses 3 operational amplifiers. 2 input amplifier is connected in the non-inverting follower configuration, and the third amplifier is connected as a simple differentiator or subtractor amplifier circuit. Instrumentation amplifier has a better CMRR, a better input impedance, high input impedance as compared to the normal differential amplifier. A key function of instrumentation amplifier is to condition small differential signals in the presence of large common mode voltages and DC potentials. So instrumentation amplifier are designed to reject the common mode voltage, VCM, and only gain up or condition differential input. Okay, so it reject the VCM and it amplify the differential voltage sense between negative terminal and positive terminal. Okay, so how much error is passed to the output by the common mode voltage is determined by the CMRR specification. Instrumentation amplifier are essentially derivative of the differential amplifier with high impedance buffer on the input. So differential amplifier should only amplify the differential mode signals and reject the common mode signals. This is true for ideal amplifiers with ideally balanced resistors. Okay? So the keyword here is ideally balanced resistors. Okay, so practical application have to take into account not only the common mode rejection of the amplifier, but also the error associated with the resistor mismatch. So what does it mean here? This is the differential amplifier configuration op-amp. So we have R1 and RF here. So the matching of RF and R1 is a major factor in the the CMRR of the differential amplifier. So this is important, the matching of RF and R1. So let's say we have a resistor tolerance of 1%, so meaning that it have a very high tolerance. We can measure the CMRR is only up to 34 decibel only. Okay, not very much. But when we reduce the resistor tolerance to 0.5, 0.1, we can see that there is a better CMRR, so about 40 decibel and 54 decibels. So if we use smaller tolerance, 0.01%, we have a 74 decibel CMRR. Normally for the instrumentation amplifier, we have a very high CMRR, I think about 120 to 140 decibels. Okay, you can see that the difference between the resistor tolerance that make the CMRR. So the lower the resistor tolerance, meaning that the resistor become more precise. So more precise meaning more expensive. Okay, actually we can do the instrumentation amplifier using 3 op-amp in the laboratory, but I think it is difficult for us to achieve instrumentation amplifier commercially available that comes in a chip. Okay, because we need to consider of this resistor tolerance. It is not a cost effective, I think, to have the same CMR for the commercially available in a chip as we compare to the homebrew instrumentation amplifier that made of 3 op-amp. So this is one of the examples of the instrumentation amplifier diagram. So we have 8 legs here. So 1, 2, 3, 4, 5, 6, 7, 8. Right. So the matching of RF to R1 is a major factor in the CMRR of the differential amplifier. And the advantage of using the commercial instrumentation amplifier instead of homebrew instrumentation amplifier made from 3 op-amp is that in order to meet the out-of-the-box CMRR specification of the commercial instrumentation amplifier, the designer need resistor match to at least 0.02%, and the input op-amp also need to be matched. It is a heavy task for us to match all these things. Component match to 0.02% are expensive in terms of time or of money. Okay, we need to spend a lot of time to configure the matching of the resistors and also the input op amps. Okay, so not worth it. All right. So this is instrumentation amplifier. So I have a separate video for this instrumentation amplifier where I explain about how to derive to come up with the V out, to calculate for the V out of the instrumentation amplifier. So just take a look at the video, and if you have any problem, you can contact me via WhatsApp, or you can ask me by coming to my room. So this is the V out of the instrumentation amplifier. So we have V out equals to AV. AV is the gain, V2 minus V1. So we have V2 minus V1. So it is actually the difference between V2 and V1. And then V out, we amplify the difference between these voltages, V2 and V1, by the factor of AV. So what is AV? AV is 2 R1 over RG plus 1 multiplied by R3 over R2. Okay, so we can see that in this equation we can have predetermined value of R1, R2 and R3. So if we have a variable resistor RG, so we can play around with the value of gain here. Okay, so that's why when you see for example, 8620, you can see that it gives you a simple equation of how to calculate the gain by only varying the value of RG. Alright, so the input stage of the instrumentation amplifier must be high input impedance mega to giga ohm typicals can have differential gain, so no common mode gain. Okay, so this is the input stage, and then the differential stage or the gain stage, it has differential gain and low input impedance. Right. So this is another one diagram. This one is instrumentation amplifier INA128. INA128 from the Texas Instruments. And you can see that the gain is defined by this equation 1 plus 50 kilo ohm over Rg. For 129 is 1 plus 49.4 kilo ohm over Rg. So when you play around with the value of Rg, you will get a different value of gain for this instrumentation amplifier. This is another one, but here it has a capacitor here. So this is used to eliminate the DC and low frequency in the first stage of this preamplifier. This one it is called as directly coupled quasi high pass amplifier design. Okay, so I took from this paper, Song et al. In 1999. So the advantage of using this kind of design is that it can maintain high CMRR of the DC coupled high input impedance instrumentation amplifier here. These are the advantages of using instrumentation amplifiers. The first one is the ability to obtain high gain with low resistor values, and a gain setting achievable via adjustment of gain resistor. So we see just now we have Rg here, so we can have a different gain setting by just adjusting the gain resistor here. And the next one, extremely high input impedance, superior rejection of common mode signals, less performance deterioration if the source impedance changes. Okay, if the source impedance changes, because it has a very high input impedance, the performance does not affect by the variation of the impedance changes into the input, and also it is a low power consumption. And if we can add more, maybe number 7 is a low bias and offset current, and the last one maybe high slew rate. Okay, so this is the advantages of the bipotensial amplifiers.